Yeah. Okay, so that's our last speaker today, Yves André from CNR's France. He will talk about the direct sum and theorem and beyond.
Thank you very much. Let's see. So the direct summand theorem, which is a statement which was proposed by Hochster, is a statement in commutative algebra, which belongs to a part of commutative algebra, which is not exactly the degree zero or chapter zero of algebraic geometry. So, as many people believe, commutative algebra is just chapter zero, the solfeggio of the music of algebraic geometry. But it is not exactly the case. There are some statements, like this one, which I will recall, that are not immediately understandable for a classical algebraic geometer, although it is completely easy and immediately possible to state. It deals with finite coverings, and finite coverings are very important in algebraic geometry, because if you neglect finite coverings, everything in algebraic geometry, every sequence of nested subvariety of an algebraic geometry is just like a flag of vector space. So it's not a minor detail to understand finite coverings in a fine way. And so the direct summand conjecture, which is now a theorem, is such a very general and elementary looking statement concerning finite covering of regular schemes. And in fact, it says, I can state that if you have a regular ring, commutative ring, and a finite extension, finite in the sense of module, but an algebra which is finite over this ring, then it should split in the category of module over the small ring. So that's a very elementary looking statement, but it looks strange from the viewpoint of algebraic geometry. What does it mean that a finite extension splits in the category of modules? So this is essentially the aim of this presentation, to explain that actually this has a deep geometric meaning. And I will review this statement, but also other related statements, which in the original formulation by Hochster looks even much more mysterious for algebraic geometry, but which are very much geometric in essence. These statements, in general, have been, so I have proven them in general. In general means in the difficult case, which is mixed characteristic, using new techniques which come from p-adic theory, so not techniques from classical commutative algebra. But I will not emphasize the techniques or proofs themselves, but rather the geometric significance of this statement. But also, I will nevertheless say some words about why p-adic theory enters the picture. But I will start with some very elementary comments about base change. So if you have a ring map, it's alpha, so R to S is induced a base change functor, alpha star, between R modules and S modules. And this functor is exact, respectively faithful, exact, respectively faithful, if and only if, by definition. So alpha is flat or faithfully flat or pure. But pure is a poor relative. So almost nobody used this, although it was introduced by Bourbaki at the same time as flatness or faithful flatness. And so you see that faithfully flat is, by definition, flat plus pure. An elementary fact is that a pure morphism, so which by definition means that the base change is faithful, is so alpha is pure if and only if it is universally injective, which means that it remains injective after any base change. So if you replace R by some extension. So since it is not a well-known concept, I will list some criteria. So the first obvious criterion is that if alpha splits, then in the category of R modules, then it is pure. But the converse is also almost true. It is true under some conditions. For instance, in the case where S is finitely presented as an R module, or else if R is complete, but yet local ring. There is another very old criterion by Bourbaki that if there exists some S module M, which is faithfully flat over the small ring R, then the ring extension R to S is pure. I will comment later about the converse of this. So now let's come to reverse base change, that is descent. So the main concept in this context is the concept of descent datum, which is that of an S module N plus an isomorphism between the tensor product S N tensor S and S tensor N, which satisfies the usual cocycle relation. Those descent form a category. The objects are the N and the isomorphism phi. And the base change factors through the obvious functor C alpha, which associated to any R module, M, let's say, M tensor S, with the obvious descent datum. And then when you forget the isomorphism phi, so the composite term is exactly the base change functor. So now in this context, Grothendieck's usual descent theorem is that if alpha, the ring map, is faithfully flat, then this functor C alpha, which associates to module its descent datum, is an equivalent. But it was a not so well-known discovery by Olivier, Jean-Pierre Olivier. Also, the author himself is not so well-known, which dates from the 70s, right? That in this story of descent, flatness is completely irrelevant. So faithfully flat is flat plus pure. And what is relevant is pure. So Olivier's theorem is that, in fact, alpha, the ring map, is pure if and only if the functor C alpha, which is associated to a module, R module, the descent datum, is an equivalent. And this is also equivalent that C alpha is fully faithful. So, well, it's not very well known, also because it was published, the cryptic note au compte rendu, without proofs, only some indications. So, it was long overlooked, and we discovered with some other proofs. So in a paper with Louisa Fiorot, we tried to reconstruct this proof according to the indication in this note, but it's difficult to be sure that it was really what Olivier had in mind. But fortunately, we asked Daniel Ferrand, who was a close friend of Olivier, and remembers the proof. And So it confirms that so what we have done are just giving the detail of Olivier's proof. So now the point is that what is the geometric interpretation of purity? So I will comment about the geometric meaning of flatness, of course, it's well known. Also, faithful flatness, but purity. So it turns out that it is best expressed in terms of some Grothendieck topologies. So I will say a few words about Grothendieck topologies. So if you have a category C, which has initial object and fiber one initial object and all fiber products, for instance, the category of affine scheme over a commutative ring K, this will be my main example, Fk. Then you can consider, the Grothendieck pretopology is a class of morphisms which are called covering families in C, which contains all isomorphism, which is stable by base change and by composition. And Grothendieck pretopology is called a topology or saturated if any family defined, which is a refined covering family, is itself a covering family. So now some examples which will matter in this talk. The FPQC pretopology on the category of affine K scheme. In this pretopology, the covering maps Y to X are the faithfully flat maps. Now, what is the FPQC topology? So this is just a saturation. So a map Y to X between affine K scheme is a covering map if and only there exists some Z over Y such that the composition Z to Y to X is faithfully flat. But Y to X is not necessarily fully flat. Another example is the effective descent topology, in the same category. The covering families, by definition, are those for which the corresponding functor C alpha of the last slides are equivalents of category. And there is another topology which exists on any C, the canonical topology. This is the finest Grothendieck topology, such that all representable pre-sheaves are sheaves. In the case of the category of affine K scheme, this can be described explicitly because of this basic fact. The morphism spec S to spec R is a canonical covering, so it's a covering for the canonical topology, if and only if the map R to S is pure. So this is a geometric interpretation. But by Olivier's result, one has also the fact that the canonical topology coincides with the effective descent topology. So canonical topology, effective descent topology, and purity, in this sense, are all the same. Now there is a not so trivial remark, which is due to Reynaud and Grusson, is that the FPQC topology, of course, is coarser than the canonical topology, but it is strictly coarser. So now let me turn to finite coverings, my main topic. By finite coverings, mainly between affine K scheme, I mean finite surjective morphism. And the main question is what is the behavior of finite covering with respect to Grothendieck topology? I was speaking about the canonical one or the FPQC. So to tackle this question, let's look at example, varying the assumption and varying the request. So let us first look for examples of non-canonical finite coverings. So finite coverings which are not covering for the canonical topology. Then to find such an example, it suffices to take the normalization of any non-normal excellent scheme. For instance, if you have two crossing lines, which correspond to this map, and you normalize, so the level of the ring of functions is just this. This is not pure, because if you reduce this ring modulo the ideal x minus 1, this sends x, which is not 0 here, to 0 here. So it's not universally injective. So this is a basic example. But now you might want to have an example with x normal. This exists, but it's much more difficult to find. So the first such example was is this one. So it was given by Marie-Josée Bertin. So Y, the covering space, is just an affine space with 4 dimensions over K, which is a field of characteristic 2. And X is a quotient of Y by the cyclic action of the permutation of the variables. And why is it not example? Because the point is that X is not Cohen-Macaulay. This is Bertin's theorem, whereas any finite covering, canonical covering, always descends the Cohen-Macaulay property. It's very easy to see. So, but it is in characteristic 2. Is there any such example in characteristic 0? No, there is no such example in characteristic 0, because if X is normal, any finite covering in characteristic 0 is canonical, because you can always, you can assume that the corresponding ring, extension of ring is an extension of integral domains, and then there is a trick of taking the trace and dividing by the degree. This gives a splitting, linear splitting. So in characteristic 2, in example, this degree was the multiple of 2, so it was forbidden. So now one can be more ambitious and look for such an example of a non-canonical finite covering with X regular. Then this never exists. So this is the main theorem. So the first theorem is that any finite covering of regular scheme is canonical, hence an effective descent morphism. And due to the above interpretation of purity, which I just explained, this is the exact geometric translation of the Dirac summand conjecture theorems. Any finite extension S of a regular ring R splits as an R module. So this was proven long ago by Hochster when there is a base field in the story. Let's say when my K is a field, by commutative algebra techniques, in fact in characteristic P. This is using Frobenius, or maybe going to the inseparable closure before using Frobenius. And so in characteristic 0, this is this simple trick of dividing the trace by the degree. But in characteristic P, this is more subtle. And in mid-characteristic, so I prove it in using this perfectoid techniques. Maybe just a word of why the perfectoid techniques come into play. Because so the idea is to take inspiration of the simpler, much simpler characteristic P case. And in characteristic P, all variants of proofs use Frobenius. And Frobenius a great number of times. So it's better to go to the inseparable closure. And so the analog in mixed characteristic of this operation is to take some kind of perfectoid closure. And it turns out that this works, but it is much more technical. So now let us look at finite coverings, which are covering for the canonical topology, but which are not covering for the FPQC topology. The simplest example is the quadric cone. So you take a field of any characteristic different from 2 now, and the y will be the affine plane, and the x will be the quotient by the action of so the xy goes to minus x minus y. So there is an obvious splitting, and so the extension R to S is pure. So this is a canonical covering, but it is not a covering for the FPQC topology. To prove that it is not a covering for the FPQC topology, you have to prove that there is no Z which sits atop spec S, so that the composition is faithfully flat. And this is not so easy, in fact. It's rather tricky, but one can prove something even more, that there is no S module, not only S algebra, no S module, which is faithfully flat over R. So this gives a counterexample to the converse of Bourbaki's purity criterion. So this question of this converse was asked a long time ago by Daniel Ferrand. So this is in a paper with Ferrand. And going further, one can ask whether there is an example with X regular, and again, there is no example. Next theorem is that any finite covering Y of a regular scheme is a covering for the FPQC topology, which means that there exists a faithfully flat composed map, so there is a Z over Y, such that the composition is faithfully flat. So this is stronger than the theorem 1, because it says that this is a FPQC covering. Theorem 1 says that it is a canonical covering. So this was proved again by Hochster and also Unicky together in the presence of a base field, and in the same paper using the same kind of perfectoid method, I prove it in general. Some remarks. But in this context, the map is a covering when X is regular. If I look not at the FPQC topology, but at the FPQC pre-topology, which means the covering for the FPQC pre-topology is that Y to X is faithfully flat, then it is equivalent to say that Y is Cohen-Macaulay. So this is a restriction. So in general, finite covering of regular scheme are not covering, of course, for FPQC pre-topology, but they are always covering for the FPQC topology. The second remark is that this theorem is much stronger, in fact, than the first theorem. Already in characteristic 0, so in characteristic 0, the first theorem is trivial. This is just this trick of taking the trace and dividing by the degree, you get a section, linear section. Here, to prove that there is always this Z, so that Z over Y over X, the composition is faithfully flat, to find this Z is really difficult. And in fact, there is no other known proof than using reduction to characteristic P and some ultra-product techniques. So the characteristic 0 case of theorem 2 is more difficult than the characteristic P case. And of course, the mixed characteristic is even more complicated. So the third remark is that now one knows, so quite recently, in fact, that there exists in all cases a canonical choice for Z, or for T, which is a Ringo function of Z. This is this, where R plus denotes the absolute integral closure. So this is the integral closure in some fixed algebraic closure of the field of fraction of R. Assume that R is integral, the domain here. And the roof here is for p-adic completion in the mixed characteristic case. So this was proven by Hochster and unique in characteristic P, and it was proved recently by Bat. It's still not published, I think, in mixed characteristic using some very recent, not only prismatic method, but also his work about Riemann-Hilbert in characteristic P with Lurie and a lot of other things. So it's kind of it's a new stage of the perfectoid theory. The usual perfectoid theory is in a world of almost mathematics, and in some case, with these new techniques by Bat and others, he is able to prove under some conditions, for some context, that what one knew to be almost zero is actually zero. It is really hard work. Anyway, one has this model which always works. There's a remark that I spoke about the canonical and the FPQC topology, but there is also the FPPF topology, which puts some condition of finiteness, some notariality or something. And one could ask, is it true that a finite covering of regular scheme are covering for the FPPF topology? And this is wrong. For instance, already if X is a affine space of dimension 3, now it's easy to construct some counterexample. What this means is that the flat covering space Z over Y over X is not expected to be a finite type in general, and not even notarian. You see, for instance, that the universal answer in the mixed characteristic case or in characteristic P, this is a very, very big ring, so it's not notarian. So this theorem 2, originally it was not formulated in this geometric way. It was formulated as a conjectural existence of Cohen-Macaulay algebras. So let's say that we can always reduce to the case of where S is complete local, the finite extension of a regular R, which is also complete local. And then S algebra T is Cohen-Macaulay. So if, by definition, if every second sequence in S becomes regular in T. But when R is regular, this is equivalent to space fully flat over R. So this is why this we can find this second theorem called the existence of a big Cohen-Macaulay algebra. Big because they are not expected to be of finite type, nor even notarian in general. So what are the motivation and the application for these theorems? So the original motivation was a set of conjectures called the homological conjectures, which were due to Peskin, Spiro, Hochster, and other people, which dealt with intersection numbers or with resolution of some modules, which were kind of, so what can one say, beyond this characterization by Serre of regular ring, as a ring which have the finite projective dimension property for the residual field. And well, there is a very, very long list of homological conjectures, and now they all follow not exactly from these two theorems, but from the two theorems and a weakly functorial version of the second theorem, which is also proved now. When I say all of them, some in commutative algebra will object that it depends what you call a homological conjecture. If there is this famous conjecture of positivity of intersection number by Serre, if you put it in the list, then it is still open. This is the only one which is still open in this circle of conjectures. But another motivation, and also so the domain of application, which is very lively now, which has been opened by proof of this conjecture, is the study of singularities and also of birational geometry, including the minimal model program in mixed characteristics. So now increasing number of people work successfully on this topic, but the two persons who initiated this were Lin-Chuan Ma and Schwede, and I will try to describe their main idea. The idea is that in characteristic 0, so one usually looks at resolution of singularities of y, let's say, which I denote by pi, y tilde to y spec s. And then we have this theorem of Grauert and Riemann-Schneider, which can be written under local duality as a vanishing for local cohomology, vanishing of this shift, the higher direct image of the structural shift of y tilde, when I is less than the dimension of y. But this looks exactly as a cohomological criterion for Cohen-Macaulayness. So it means that this behaves exactly like a Cohen-Macaulay S algebra, but it is not an ordinary algebra, it is an algebra in the derived category. So the idea of Ma and Schwede is just in mixed characteristic to replace this fundamental object by the Cohen-Macaulay of OZ, where Z is this top to space, which is testfully flat over X, because in this case, as I said before, this would be, O of Z would be a Cohen-Macaulay S algebra. And it turns out that this works. And this works especially well because one can always choose, in the mixed characteristic case, O of Z, which I denoted by T previously, to be a perfectoid algebra. So not only it is testfully flat over R, but it is also perfectoid. And this is strongly used in this study of singularities in mixed characteristic. Okay, so I just mentioned briefly the weakly functorial statement. This is what you can imagine. So one starts with the diagram where the vertical map are just finite coverings of regular rings, regular space here, and one has a commutative diagram. Then the theorem says that one can complete with the Z here, so that the composed map is faithfully flat here too, but one can achieve to find a map between the Z prime and Z. this is much more difficult to prove than the theorem 2, but this is the same spirit. Now, a general question, since I discussed canonical topology and the FPQC topology, and theorem 1 and theorem 2, and I said the theorem 2 is much stronger than theorem 1, nevertheless, one can ask the question, is the canonical topology, from the category of affine space over K, generated by the FPQC topology plus something, and the something are the morphism, which, such as the structure splits as modules. I don't know the answer in general, but it is true if the base is Noetherian. So the distance between the canonical topology and the FPQC topology are just a split. So now let me come back to finite coverings and the canonical topology. There is a definition which predates all these new developments. It's the definition of a splinter. So bring R, or Noetherian affine scheme X, spec R is a splinter if for any finite covering of X, so if any finite covering of X is canonical, which can be translated in pure commutative algebra if any finite extension R to S splits as R module. So whence the name splinter. There are some general properties that any splinter is normal, so it's not difficult to see. And the theorem 1, so the direct summand theorem, says that any regular X is a splinter. So the question is, are there any other splinter? So the answer is yes. We already saw that in characteristic 0, any normal X is a splinter by the dividing the trace by the degree trick. In characteristic P, this is not so easy to see, but there is a whole collection of singularities, strongly F-regular singularities, which are splinters. So they are not regular, but I will not give the precise definition. Just this is the characteristic P analog of the log canonical singularities in the minimal model programs. And for instance, the quadric cone, in characteristic different from 2, is singular, but it is a splinter. There are a lot of examples, but the main supply to find splinters, which are not necessarily regular, is the following recipe. So X is a splinter if there exists a canonical covering Y of X, which is regular. So now it is Y which is regular. X is maybe not regular, but if Y to X is a canonical covering, then X is a splinter. In that case, by the weak functoriality of Cohen-Macaulay algebras, X is always Cohen-Macaulay. And in particular, one finds that if S is a regular ring, and the smaller ring is a direct summand of S as an R module, then it's Cohen-Macaulay. And in fact, it has only rational singularities. So this is a generalization in mixed characteristic or characteristic P of a statement which is very well known and due to Buteau, I think, and Hochster in characteristic 0, which dates from the 70s and the 80s. And the last property I would like to mention is that splinters in positive or mixed characteristic are always Cohen-Macaulay. So this is a difficult result. This is a consequence of this theorem that this R plus hat is always a big Cohen-Macaulay algebra, which is a very difficult theorem in mixed characteristic Recall that in characteristic 0, this is not at all true because any normal x is a splinter. There are some x which are normal and not Cohen-Macaulay. So now, natural question. What happens if in the definition of splinter, we replace the canonical topology by the FPQC topology? So one could call them the FPQC analogs of splinter. I mean, what can be said of those x such that any finite covering of x is a covering for the FPQC topology? Well, it seems very likely that you find, in that case, only regular. I will say will give some small evidence in this direction. But I turn back to my comments that there is no need to comment about the geometric meaning of flatness or faithful flatness in geometry, because in fact, after this reflection, I think there is a lot to say about. Because, in fact, in EGA, as you know, one finds many properties of schemes and morphism which descend along faithfully flat morphism, which means with respect to the FPQC pre-topology. But you find almost nothing about properties of schemes or morphism which descend with respect to the FPQC topology, which is much stronger. So the question is, which properties descend with respect to the FPQC topology? Only with respect to the FPQC pre-topology. Two examples. In characteristic P, so there is this famous Kunz theorem that X is regular if and only if the Frobenius map is faithfully flat, which is a covering for the FPQC pre-topology. But it can be proved, it's not difficult, that in fact you can replace in this statement, you can enhance Kunz theorem a little by replacing pre-topology by topology, FPQC topology. So, but then this implies already that if in characteristic P, and well, at least if the Frobenius is finite, which occurs very often, then all FPQC analogs of splinter are regular, as I conjectured before. Another property, which has been established by Ma, in full generality, is that regularity descends with respect to the FPQC topology. This is not obvious at all. It uses some criteria by Ma, Iyengar, and Bat, used to give some mixed characteristic analog of Kunz theorem in perfectoid terms. Using this, Ma proved that regularity descends with respect to the FPQC topology. So you see that this is in the same spirit as the Grothendieck results. Regularity descends with respect to the FPQC pre-topology, but it uses much more sophisticated tools. So, and this implies that the main supply of splinters, which I described before, so the thing which have a covering, a canonical covering, which is regular, you cannot provide in this way non-regular FPQC analogous splinters. So that the two natural examples that you had before to construct, example of a non-regular splinter, then these two methods are ruined by this. So, but anyway, this general question, which property descends with respect to the FPQC topology, is still largely open. It could be addressed in the 60s, and it brings us back to the fundamental problems about base change and descent I started with. Thank you very much for your attention.
non-commutative analog of homological conjectures. I mean, I think parallel techniques work there.
Well, there are some, this is a huge domain, so there are some analogs, so, and we have some talks, I think, in this conference. For instance, Oyama works on this topic, there are a lot of other people. This is a huge field, and in fact, personally, I learned about the direct summand conjecture in a discussion about the non-commutative analog. Then I was surprised, and then I asked, well, but in the commutative case, well, in the commutative case, this is the direct summand conjecture. I did not know the direct summand conjecture, so I learned it through by frequentation of the non-commutative case. This is just anecdotic. But there is there is a whole skein of conjecture which are rather parallel to the homological conjecture.